So, right, testing a claim about a mean, right? Test the claim about a mean using the terminology, right? So here's some of the key concepts, right? The most important method is when standard deviation, population standard deviation is not known. That is much more common because we are testing a claim about, because we're saying we don't know the population mean, right? Otherwise, why would we be testing a claim about it, right? If we knew it exactly. So we probably don't know the population standard deviation. It would be unusual for us to know it, right? So that means what distribution do we use when we do not know the population standard deviation? What does that mean? We do, yes, but that is a bias estimator. So what distribution do we have to use? We use this the same thing when we calculated a confidence interval for the population mean. That's not a distribution, though. We use a normal distribution. That would be great. We'd use normal distribution if we knew the population standard deviation. We could use that, but we have to account for the fact that we don't. So there's more error. There's a larger possibility of being off by more. T distribution, right? Okay, this guy's, I've said this 4 or 5 times, right? But I want you to remember this. When we did this in the confidence intervals too, right? We had to find our critical values. Review that confidence interval stuff. We spent a lot of time doing that, right? If this is known, that's the Z distribution. If it's unknown, that's the T distribution, okay? It's a big, important thing to understand. Which of these distributions has wider tails, T or Z? T, absolutely, because wider tails means more variation, right? So the T distribution has to have more variation because it has to consider the fact that S is a biased estimator, right? It's less biased largest our sample size is. So the closer you are to if you have a very large population, you're not going to get a big difference between a Z and a T. But if you use a small one, you definitely need to. Because remember, for a T distribution, you need to account for what that you don't need to for a Z distribution. You have something called the degrees of freedom, right? You have to take that into account. Okay, so that's the sample. This is what I was saying here, right? So that's where you're going to use most of the time. Again, these are the steps you're going to go through for the critical value method. And this is the same. What's the only real difference here in this one than the one we use for a proportion? These steps. Matilda, I think you told me. Think something will say that again? No. Step 4, and what's different about step 4? The formula, right? Because the test statistic is T instead of Z, and it involves means and stuff as opposed to proportions, right? Now, what I think you're thinking about, Bobby, is that there are 2 different methods that had steps 5 and 6B, right? So within the proportion, there is the p-value method and the critical value method, right? So those 2 were different in steps 5 and 6. This is the same. This is a critical value method, so it's identical to the previous critical value method, except for it uses T. So you were correct, but you're answering a different question, if that makes sense. Okay. So here's the problem that we had, right? We checked the requirements. Okay. So let's just reminded what we did, right? So we have this thing, right? Step number 1 is you always look at your original claim. We decided, right, in this scenario, it was like, hey, people, are they not sleeping enough? I know I'm not sleeping enough. I got like 4 hours of sleep last night because I procrastinated. I wrote this, and I wrote 2 celebrations last night, so I was up a while. So I was surprised that happened. Well, ChatGPT helped me write. I can use ChatGPT to write the questions. I can't. You can't use it to answer them though. That's a little different. And trust me, when I say I used it, I had to change them a lot because it does weird stuff. Yeah, and it would forget to include things. Like it would do these, but it wouldn't. It would like. It was funny. It would include it, and it would say it would give an answer, and it wouldn't give like the. It wouldn't give p. It would say assume p is 0.5, and I'm like, why would you do that? You need to say that, right? Okay, so you have your claim, null hypothesis, alternative hypothesis, significance level. Then you calculate your test statistic. Okay, so let's do the next step. So let me just, so this is the t-value. We'll do a couple of these, all right? Just want to make sure I have all my numbers here, right? So pull that bad boy out. Okay, so now that we have all the information we need, what do we need to do? What's step 5 for the critical value method? So let's take a look since you guys have forgotten. It's you sketch the curve and identify the critical values in the critical region. So let's sketch the curve. This is a t-distribution, right? But t-distribution looks an awfully lot like a z-distribution when you just draw it out because they're both bell-shaped, right? So now, when we're looking for the critical area, right, that depends on the significance level and whether it and the type of tail, right? What type of, so we remember before we had a left tail test. So you need to draw out your curve, right? The left tail test means that we want to find this. So this is our critical value, right? What do we want that area to the left to be? We did this many times. So that's based on the let me remind you. So we only want to is the area in one tail, but what should it be? That's absolutely right. Thank you, Myra. So it's supposed to be the significance value, right? Because we're saying I only want to reject my null hypothesis if I'm pretty sure, right? I want a 5% significance level. That means I want to be 95% confident. So I only want to reject it if there's a less than 5% probability something like this would happen by random chance, correct? Is everyone understanding? So we need to figure out this critical value of the statistic t that separates the bottom 5% from the top 95%, okay? I'll show you how to do this on your calculator later, but let's look at our table. So let's go to our t-table. Does everyone have their table with them? So now we're going to use this table a little bit differently than we did before. So before we were creating a confidence interval, right? And the mean was always in the dead center of the confidence interval. So we were always looking at two tails, right? We always wanted to have like the tails there. But in this case, we're only having a tail on the left. So everybody, what is the area that we want to be to the left. We just drew it out. Does everyone remember that we said 0.05? So should I be looking here or here? On the middle column or the one just to the right of that, everybody? To the right, and how did you determine that? Because you're correct. It could be, but it's not this case because I said, are we doing a left, right tail test or two-tailed? Left. So left tail means only one tail, right? So the area in one tail should be, this area should be 5%, right? So that's what we're looking for. Now, how do we determine the degrees of freedom? Easiest formula in this class. N minus 1. I hope you all can do that. And I believe there were only a pretty small sample, 12 people in it. I guess it's hard to collect sleep studying from there. So we go to this. And this is our critical value. Does everyone understand how I found this? Identified, right? So in this case, you have to think about, right, am I thinking about area in one tail or two tails? I haven't done a two-tailed test yet, so you don't know where it's coming up. The next test I will do will be two-tailed, so you'll have seen at least one of them, all right? And then we'll do some more hypothesis tests. Okay, so that's my critical value, so I'm going to write that down, although it's not exactly my critical value. So the number that I got from my table it said T critical was negative 1.7. Well, actually, I didn't. It said it was, let me tell you what it said. It said it was positive, right? But guys, that doesn't make sense because our critical value is to the left or the right of center? To the left. So it should be, everybody, we get why it's negative. I'm not getting, some people are not even looking at me right now, so please pay attention, right? It should be negative, right? The table assumes it's to the right, but that's okay because this thing's symmetric, right? So that's our critical value, right? Now, we want to then, once you have your critical value on there, you want to then sketch your test statistic. What did we calculate our test statistic to be here, y'all? It's right up here. Everybody, our test statistic is 0.300, but not just 0.300, it's, yeah. So that was the t-value that corresponds to our population mean, right? That tells us our population mean is a t-value of negative 0.3. So where did I draw that? That would be, so it's negative, so is that to the left or the right of the center? It's to the left, but now compared to the critical value, is it going to be like here, or is it going to be over here? Here, number one, or option number two? What is this critical value right here? Yeah, no, so this is, the area is 0.4. The critical value is negative 1.79. Our test statistic is negative 0.3, so it's not quite that far left, right? Everyone's seeing this. Please just ask questions if you don't understand why I put it there. It's just a number line, right? Not quite as negative. So step 6 is to decide whether what? I either accept or reject the, guys, what's the whole purpose of hypothesis testing? It's to test the hypothesis. So step 6 is to always or fail to reject, right? Okay, so where is our critical, so our test statistic, is it in the critical region? Just look, test statistic, critical region. Everybody, yes or no? No, right? We see this? This is the test statistic is right here, right? Because the test statistic T is only 0.3. We want to know, right? We want it far away from average, right? Thus to reject, to say this is unlikely to happen by chance. It is not, right? Anytime you're not in the critical region, you reject, or you fail to reject, sorry, right? You're not doing anything. This is not interesting. So, test statistic is not in the critical region. So that means fail to reject the null hypothesis. So our conclusion would be there, you either say there is or there is not sufficient evidence. So we are not rejecting. So is there sufficient evidence, guys? No, right? So we say not be able to fit the claim, right? And the claim here is that the mean there's not sufficient evidence to, okay, let me write it this way. So we're not rejecting the null hypothesis, right? So there's not sufficient evidence to claim mu is less than 7. So let me just kind of go why that's the case, right? So we have this study, right? We're told you need at least 7 hours of sleep on average to be healthy, right? What we found here is there is not, right? Now, it seems like, okay, this mean is less than 7, right? But it's not much less than 7, and the sample size is small. So it seems like this could have easily happened by chance. Does everyone follow what I'm saying? But we're not sure. When we did this test hypothesis, we weren't able to reject the claim, right? So we don't have overwhelming evidence to reject the claim that it's not equal to 7. So we don't know that it's less than 7. We don't have overwhelming evidence to support that it's less than 7. Because it's not, the sample mean isn't far enough away from 7 that we can be sure that it didn't happen by chance. Does that give us some intuition here? Okay, so any questions? Please ask questions if you're not following along. Okay, so here's one that might be a little bit different. Okay, so let's read this. So our book has an appendix B, and it has, well, right, so these are the statistics for measuring body temperature, right? And it gives us n is more than 106. We have the mean, and we have the standard deviation. Now that standard deviation there, is it the population standard deviation or the sample standard deviation, the one that's quoted? Sample or population? It's the sample. You can tell because it uses the lowercase s for 1 instead of sigma. 2, right? It's referring to a data set, right? Like it's clearly a sample, right? And that's what it's going to be almost all the time. Again, since we do not, so do we have the population standard deviation class? Which means what distribution do we use? I just said this and I underlined it, emphasized it. T, you always use T when you do not have sigma, okay? But first, before we even do this, we need to check to make sure that this fits the requirements for us to do a distribution, right? The first requirement is that the sample must be a what type of sample? This has always been true. Random, and not just random, it needs to be simple random. Okay, so that is, let's just assume that's true, okay? What is the other one? It's an or. This distribution needs to be normal. We need to know it's normally distributed, or yes. And in this case, it is. So yeah. So it's 30 or greater. It's a lot greater than. So we can just jump into it, right? If it was 25, we would say, okay, I'm not sure we can do it, but we might be able to if we know the distribution is normal, right? So now let's jump into this, okay? Let's just go through each part. So step 1, everybody, is to write the say that again? The original, yeah, like kind of the original. What's the person thinking, right? So this is the more interesting one, right? So they are saying they are testing the common belief, right? This one's different. So notice they're saying test the common belief. So that means that this author just doesn't believe this study. So this is for the first time. So remember, the original claim is always going to be some sort of inequality. And before, it's always been less than or greater than. What's it going to be in this case? If you don't see any evidence pointing towards one or the other, it's probably this. It's not equal to, because it just says, this is our study. We are told this. This is the claim. You're just skeptical about the claim in general. You don't have any feeling, right? Like certain types, it would be catastrophic if, right, your mean, if you thought that the mean was too low, that would be significant. But if it's too high, it's not. Here we're just saying, I'm not so sure about this claim, right? I don't think I think there's something wrong with the study that has this claim. I don't know which way it's wrong. If the body temperature is significantly higher or significantly lower, it would both disprove this claim, right? So in that case, it's a not equals to. Okay, so that's the original claim. That's kind of hard to get out of there, right? And that came from this. Okay, 2, everybody, is to identify something else. At this point, you shouldn't be having to turn back, but it's okay, right? Because so this is the original claim, and we need to have a null hypothesis, which everybody always has a. So in this case, the null hypothesis would be mu is, yeah, right? And it's not going to be this because that's the sample, right? Like that's not. Okay, so that's H naught. And then the alternative hypothesis here would be that it always involves an inequality. So it's going to be less than, greater than, or not equal to. Not equal to. It's pretty much, trying to think, it's going to almost always be this one, right? It's always going to be the one that's the same that's in the original claim. Okay, so for the first time, what sort of test? So we also need to identify left, right, or two-tailed. Since it's not equal to, So if it's left, it's right-tailed, right? Sorry, if it's less than, it's left-tailed. If it's greater than, it's right-tailed. So not equal to naturally would be two-tailed, right? If you are far enough away from the accepted value on either side, that's evidence in support of the alternative hypothesis, right? Okay, 3 is, whoa, always the easiest step. It is to significance level, which is easy here. It is 0.5. Step 4 is to calculate the test statistic, is what I think you just got. And in this case, the test statistic, everybody, is Z, right? It is not Z. It is, everybody. It is T because what is not known? The population standard deviation is not known. All right, I'm saying, hopefully I've said this enough times now that it's kind of sinking in, all right? When you're doing a mean, this will be the most, like almost always you use a T distribution. So you want to calculate T, which the formula is X bar minus mu so let's plug that in. So which one of these is X bar? And then mu is, okay, S is point. And then N is 106. Make sure you put parentheses around all of this when you use your calculator, okay? Anybody got a value for me? Yeah. I got 6.65. You're going to end up finding that it is so not important. Let's just try to give it a sense. Is that a lot? Is that like a lot or like not very much when it comes to like standard deviations? Yeah, that's a lot, right? Pretty much saying anything that's like above 2 is a lot, right? So just give us, right? And that seems like, this doesn't seem like a big difference. It's 0.4, right? But notice, like, the standard deviation is very small and the sample size is very large, right? So taking that all together, that's significant, right? So just guessing on this before we do anything, since we have something that's this extreme, are we going to probably be rejecting or accepting the null hypothesis? Yeah, because it means it's a lot different than what we expect, right? And that's what we're going to end up finding. But let's make sure that we do the analysis carefully. So step 5, everybody, is to sketch it. Okay. What are we going to be doing? Something very different for the first. This is the traditional critical value method, which is the only method I'm going to teach here, right? What is something very different that we have to do that we've not done before? This is special in that this one was two-tailed, okay? So if you can think about two-tailed, you're going to have something that looks like this. Now before, that 0.5, right, was the area of just one tail, right? Now it's the area of two. Now is it the area of each tail or is it the combined area? It is the combined because, right, we want to be more than, we want to be 95% sure, right? So we want to make sure that it's in the 5% most extreme data, but since, right, we don't know which way it's extreme, we want to split that 5% evenly, all right? So that means each tail has an area of point. So we need to then, right, when we're doing this, we need to figure out, is our test statistic like in, well, our test statistic was negative, right? So we need to figure out, is it in here or is it in there, right? So to do that, we need to find these. What do we need to find? What's this value that separates it called? Yeah. We're doing, it's t, but this is the, since for this case it's called the, what's the, someone said it? Critical value, right? So let's look at, right? We can only use the critical value method here, right? You can't really find the exact percentage that corresponds to it because our table is critical values. Okay, so now again, you want to be careful, right? So Fabian, you told me never use the middle column. Are you right? So we are doing a 2 or 1 tail test here. 2, and we said that the area in both tails combined was, well, that was each tail, wasn't it? Right, so either way you can think about it, right? Either way, it's actually, you are using the middle column here, right? Because it's a 2-tail test. You can either think of, right? It doesn't matter, right? You know, you could think of it maybe in as 5% in 2 tails. Regina could think of it, well, it's 5% in both, so I'm going to look for 2.5 in 1 tail, right? They could have created a tail where they just cut off one of these lines, but this way it's a little more useful because you can think about it either way. All right. And then, well, we had, what was our, so what's our degree of freedom? So what is our degree of freedom in this case? It was, it's a lot, right? 105. Okay, so now let's move over to here. We don't exactly have 105, so let's just use 100. This is, you might think that's not that, I feel uncomfortable using that. That's fine, right? If you use more, right, we're being more conservative, so it's going to be okay. You can see that. So we got our t-crit. So now we found it. Our t-critical value was, that's our critical value, right? Now, since it's 2-tailed, what's going to be this critical value over here, Bobby, considering the shape of this distribution? It's symmetric. I'll give you the hint. Yeah, absolutely, because it's symmetric, right? It has to be. Imagine you fold it over. It has to be negative, right? Then, right, once you draw this out, you have the critical values. We want to compare our critical values to our what? What did we find in the previous test step? Test statistic. Our test statistic was roughly around 6 2/3, right? So our test statistic, we did this. It's not anywhere. It would be way over. It's like over, maybe here. So our test statistic is or is not. What's the question we want to ask? Is it in the critical region, everybody? And the answer here is, yeah, not just yes. The answer is hell yes. It's way out there, right? So if you're like, we use the 5% significance level. It doesn't really matter. You could see, right? It's so far out there, it doesn't matter what significance level you're using, right? You're talking about something like there's like a 1 in a million chance or something this would happen by chance, right? So the test statistic, I'm going to say that's TS, is in the critical region, right? Which means, what do we do with our null hypothesis? Accept it? Or I guess we never accept. We either fail to reject or reject it. Which one do we do here? What do we think? Fail to reject or reject? I got 2. Well, we fail to reject when we don't have overwhelming evidence that our sample is different than our mean. So say again. Yeah, it's way different, right? You are 6 standard deviations smaller than you're expecting it, right? That is a lot different, right? You could have even guessed that before even doing this calculation, but we did it just for completeness, right? Because if I said, oh, it's 2 1/4, right? You would say, well, is that enough? Well, yes, closer to, but it would still be in there, right? That's why we calculate this value exactly, right? But anytime you're in the critical region, right? Think about extreme. Overwhelming evidence means extreme values, right? You're looking for something that is extremely different than what you would expect. And that's exactly what we have here, right? So in the critical region, right? Remember, in the traditional method, or sorry, not the probability, the p-value method, you're looking at a p-value that's very small, right? Either way, is in the critical region. So that means there is, anytime you reject, right? Since remember, your null hypothesis is kind of the opposite of your original claim, right? You might want to write this out in more words. I don't have space, right? So just kind of look at what's going on here, right? The commonly held belief is that human body temperatures have a mean of 98.6. You collected a sample that had a mean of 98.2 and a pretty low standard deviation. It doesn't seem like a big difference, but because that sample is so big and that standard deviation is so small, we found out that the chance of something like that happening by chance, right, on both sides, right, either something that's as far off as this to the hotter side, or in this case, it was the cooler side, right, the probability of that is way less than 5, right, because this is way over here. So this would be unlikely, so either you just found the 106 coldest people in the world, right, and that just happened by chance, not buying it, right? Original assumption, false. Now, there's sufficient evidence to support. We don't know, but like, this is as close you can know, assuming that there's no problem with your experimental design, right, and measurement or something along that path, all right? Questions here? Okay, so how do you do this if so my last slide, right, is if you do know, for some reason, I'll give you one example in the second half of class today. If you do know your population standard deviation, you do the exact same steps I just did, except instead of using the t-distribution, you use the z-distribution. That's the only difference. Okay, so since this stuff's important, I'm going to do more examples, and I'm going to mix it all up, right, in the next half of class. And I'm going to teach you how to use the calculator. But you should be able to do it either way, because I might say show your calculations for the test statistic. All right. Some classes focus just on the calculator because they say you can always use the calculator in real life. I grant it, but there's a good chance it might be 4 or 5 years before you use this. If you don't practice like doing it the hard way, then it's not going to stick, right? So if you want to take like, I'm going to give a 5